You then, Russ?
That's it.
Okay, well, thank you very much. I always enjoy, looking back at how we got to where we are and all the offshoots and everything that has been sparked in the projects that have come from it. So, yeah, and it's perfect that you let Dan talk for the last few minutes because he's the next speaker. And now that his voice is all warmed up, Dan Gray, you're up.
Okay, well, I'm just going to share my screen. Let's see if that works. Oh, somebody told me to do this little option, optimize screen for, we have a couple of videos.
Yes.
Okay, so F5. Whoops, back up. All right, so this talk is about building a 36 inches in F4, and it's portable, and I put that in quotes, Altaz with direct drive motors. And it went through a lot of design thought, and I finally decided to propose a direct drive system, and you'll see why in a few slides. So we're building it for Jimi Lowry. Is that how you pronounce his name?
Lowry.
Lowry. Okay, he's a close friend of Howard's, and he's an incredible observer.
Oh, yeah.
He uses high power. He won't touch a paracore because he uses high power, and the glass of the paracore might eat up a few photons and they don't go to his retina. That's kind of his philosophy. Mostly galaxies, I think. I'm going to show you a slide next of his setup, and it's near the McDonald Observatory, right, Howard?
Yeah, West Texas.
And it's called Barbarella.
Yeah.
And I'm not sure where that came from.
Well,
Do you know?
I can tell you why. Yeah. The telescope was designed and made by the OMI company. I don't know what, 10, 15 years ago, whenever it was. And when they first put it together, they found out that their weight calculations were off and the telescope was bottom heavy. So they had to put about 50 pounds of barbell weights up on the cage to balance it. And so the barbell weights, Barbarella.
Ah.
Yeah, he's got a poster of the movie Barbarella on the wall in his observatory.
Oh, okay. I get it now. Thanks, Howard.
Yeah, there you go. And
So
there it is.
There's barbells up at the top right.
Yeah, there you see it. Yeah.
Well, that's a better problem to have than the other way.
Yes.
Yeah. So I guess he's not afraid of heights, huh?
No. Well, you know what? Because he's got great skies there in West Texas, being so close to the McDonald. But when you're out there, it's a 14-foot tall ladder, and it's dark. And once you start getting up the ladder, you can't see the floor of the observatory very well. So you kind of lose track of how high it is. Plus, you just want to look in the eyepiece.
Yeah. So
48-inch telescope, holy cow.
Yeah. So Howard has flown down there several times just for observing sessions.
Oh, yeah.
Yeah. So that must be a real treat.
It is.
And can you tell us a little bit, Howard, about how Jimi observes?
Well, in a few words, he goes all out. He is about seeing things that no one else has seen visually. He's all about trying to see things that, basically would strain your belief if you hadn't actually looked through his telescope and seen some of them yourself. He wants to basically push the limits for visual observing with today's technology, and that's why he doesn't want to have he doesn't need a paracore, because he never observes at a low enough power to benefit from one. Plus, like you said, why put more glass in the light path?
Okay.
Yeah, and that's about it. He's just a hardcore, all-out visual observer.
All right. So the only problem is he's mainly used the northern skies, and now he wants to take it to the southern skies. And Barbarella won't go on the plane with him, not surprisingly. And So his idea was to ship a telescope down there, put it in a trailer, and then he can fly down there and view the southern skies. I hope to meet him there sometime. So now we're going to talk about a little history. Oh, not yet. So this is Jimmy was communicating with Tom Osipowski about building it, and Tom wasn't excited about it. It was like too big and too, he's kind of, he's got enough business, and I don't know, he just didn't want to do it. So Howard, who's a good friend of Jimmy's, put us in touch. And so we started talking about this a few months ago. So now we're going to go to the history. And I think it was 1999, maybe 2000. I built a 28-inch visual string scope. And here it is in its first iteration. You can see it has a secondary that's folded back. That's called a folded Newtonian. It's got that cute baffle up at the top that looks like a Star Trek emblem. You can see at the bottom, you can see my mouse. This is an altitude clutch. You can use it in the drag and track mode. There's also an azimuth clutch. This has all been changed since then. Anyway, soon afterward, Howard improved on my design, and he built this telescope. And you can see he had two clutches. You can see the encoder on top of that. You can see the altitude clutch over here on the left. If you can see, can you guys see my mouse?
Yeah.
Okay, good. And this is an early Altaz workshop up at our shop at Technical Marine Service. Anyway, Howard scope is outstanding in its field, and this is an incredible view, don't you think? And not only that, but I think that the telescope is pretty nice too. And Howard has continually improved this telescope over the years. He second most recently completely redid all the drives and clutches. And thirdly, and the last thing he did was a high-tech ventilation system. I think we're going to hear about that later on. And then Tom Osipowski also improved on it. And there's Tom with I think a 24-inch telescope. Well, in 2000, oh, I'd like to tell about the phone call I got from Russ Genet. And this was in the early 2000s, and he was wondering about the our servo controller for telescopes. And I'd never met him. However, I knew about him because I had that book that he and, oh, I can't think of his name right now.
Mark Trueblood.
Thank you, Russ. Mark Trueblood wrote. And, those, the formulas in there still work even today. And I used them on some of my software that I was writing way back then. And then I ended up going to that Cal Poly workshop that Russ had pointed out, and I met Dave Rowe. And what a great change in life. Really a life-changing experience, to be perfectly honest. And out of that came the Cal Poly telescope, which Russ mentioned. So after the Cal Poly students graduated and went their separate ways, we took it up at TMS to try to make it work. And I don't know how many pounds of epoxy is on that thing to get the bearing straight and replace, two bearings on each side instead of one, and make one axis point to the other axis. And I mean, fork. It was it was a mess, really. But we ended up getting it working. And so then Richard and me basically tested it at our shop at TMS quite a few nights until we felt it was okay to bring it to Richard's place. And so he built a little shelter for it, and he was testing it and having some pretty good results. And then the encoder tape broke and peeled off, and it was a disaster, and it sat around for a while, but we did fix it. And then Richard went other directions. He had other things, and so he wanted to see what I would think about doing with it. Well, I have a place to put it. I have it roll-off roof observatory that it barely fits in. And I was wondering, have you guys have heard of a takeoff roof observatory? There's a takeoff roof observatory. And there it is. There's a direct drive motor at the bottom. There's the other direct drive motor. I guess it's on that fork on the left. There's the encoder that's behind that wooden cover. I think Richard actually made that. And then it's got a focuser and rotator. And this is the model, one of the models that I made while we were testing it. Well, while I was testing it. And this is the software that Dave Rowe wrote. And he and PlaneWave are kind enough to share it with all the SciTechers out there. And this one is a 3.7 arc second RMS with 4 points turned off, you can see. And then the following image is an image of NGC 891. And it's got 3 10-minute open loop unguided exposures stacked together. And I find that incredible. And it's because of the technology of direct drives and also Dave Rowe's pointing model, Point XP. So thank you, Dave. All right, so now we're going to get back to Jimi scope. And so I was thinking about making a mount similar to Howard's and Tom's. And then, you know, we've come a long way in making motors and, you know, that sort of thing. And so I started considering doing a direct drive. And so this is what I came up with as a preliminary design. And I think that the secondary mirror needs a little more support. And so does the focuser. It's just incomplete, really. And I will get some more details real soon. So the reasons is, you know, Jimi uses high power, and it must be frustrating to go somewhere and it's not quite there, and you know you have to sync. He'll make a 16 point that's going to be perfectly enough visual model at the beginning of the night, and then if he doesn't move the scope, you can use it any other night. And he'll have perfect tracking and centering, and so why not, even if it's a visual telescope? So I tried to think of reasons not to do it, and one, it's a heavier mount, and Jimi didn't like that. He thought it was too heavy, and I kind of came back a week or two later and said, I'm worried if I make it lighter, you know, a direct drive mount has to be stiff. And so he became okay with that. So it requires a bigger battery, and it's slightly more expensive. But when you're talking about a 36-inch telescope, I mean, the mirror costs, you know, a lot. And you know, all the rest of the structure isn't going to change that much. The electronics are going to be a little more expensive. The motor is going to be a little more expensive because we have to build it from scratch. But in the large scheme of things, the slightly more expensive isn't a big deal. And a bigger battery isn't that big of a deal. So, you know, there's a lot of advantages to having a direct drive telescope. Probably the main one is accuracy. And then others are wind resistance and speed of slew, if if you care about that too much with a scope that big. Okay, so I based my design on what is called a slewing bearing, and I'd never even heard this term, but I started looking at trying to find a big azimuth bearing because you kind of need one. And I found a place, jcbbearing.com, and here's some pictures I got off their website. I didn't get permission to do this because I didn't have time, so I hope I don't get in trouble, but I'm sure it's just you know, more advertising for them. So these are some slewing bearings, and basically they're 4 contact point bearings, and instead of, you know, the balls are kind of in the gap there. I'll show you more of it. So one shortcoming of the slewing bearing is significant friction, and it's related to weight. And there's going to be about 1,000 pounds on the slewing bearing. And so I did some calculations with data that they sent me. Excuse me. And they're going to have about 20 Newton meters of friction component. a frictional component with all the weight on there. And so I was a little worried about that, and I think I solved that problem, as you'll see in a little bit. So we're going to build the direct drive motors, and we know how to do it now. And I'll show you. Okay, so we made a siderostat for the University of Arizona, and the big hollows that you see there is the light path of this telescope, and it hits two flats, elliptical flats that David Davis made, and it puts it down into the room where they're doing spectroscopy and stuff. So that's what this is about. This is Daniel. He works here. And this is our coil winding machine. So we use an airplane simulator, a flight simulator, pedals, and he's controlling the speed of the motor, the winding motor. You can see that thing is winding, and there it is, see? So every time it makes one revolution, that other one turns just the right amount. And we went through a lot of iterations of how to make coils, and this really works nicely. And you have to make sure that epoxy gets in all the windings. And we tried vacuum chambers, and nothing really had success until we did it like this. And this really works, and it's so cool. So I'm going to, for the sake of time, I'm going to advance this a little bit. And this is the software that's controlling it. And there's a configuration tab I won't show you, but it's counting the turns of each layer and telling when to go to the next layer and moving that little fishing reel setup. And I think we're done with this video. Okay, so at this point, I'm going to take a break from my presentation. There's a few more pages, but I want to show you some of the design that I've done for this telescope. And if anybody wants to interrupt me, just turn on your mic and interrupt me and tell me if you see a problem or if you see a place where I could improve. And I've got a piece of paper and a pencil down here, and I will jot down your suggestions. So here we go, interactive mode. Let's see, I want to find this one first. So this is a mirror cell. And you can see that the mirror hasn't been silvered yet. And I'm going to turn the mirror off so we can see more details. And I'm going to turn the whole shooting match off and zoom into this little part right here. Okay, so this outside part is going to be like a piece of plastic tubing, or we might 3D print something. And then the inside part is a 632 threaded rod, probably, or screw. Okay, I'll turn that back on. I'm going to just turn on okay, so this is one of the wiffle trees without the bearings on them. And I put a lot of thought into this. And it has 2 pieces of steel, 1/8 inch steel, I think. And I'll turn that off. And then it has 3 pieces of aluminum that are CNC'd. And that right there is a bearing. There's 2 bearings. And then this is a 5/8 post that's welded to the cell frame. And then there's a little spacer right here to keep it up. And then there will be a threaded, like a nylock or something at the top. So that's the wiffle trees for the edge support. Okay, so let's turn these guys off. And we'll go back to, I guess we'll turn on the whole mirror cell and start looking at it. Oh, I need to break out of here real quick and show you a couple of pictures. Okay, so this is a picture of a spherical bearing that I got from McMaster Carr. thinking I would be using that on the cell plates. 30 seconds after I got it in the mail, I realized it wouldn't work. As soon as you put weight on that, in that direction, there was so much friction. There's no way it would have ever worked. And so then I started experimenting around. I got a brass acorn nut, and what you see here is, you can't see it, but there's a hole drilled in this piece of steel, and there's a chamfer on it. So it's just a regular angle chamfer. And I can put as much pressure I want on that screw, and it still turns, or, you know, easily. So I'm sold on this. The problem is that an acorn nut isn't going to work because there's really nothing in there, and I need to tap a hole in it. So we have a CNC machine lathe, and so we're going to make them on that. Okay, so now we're back to the show here, or the interactive. So I'm going to turn on the small spheres and big spheres, and we're going to zoom in. What's that doing on? Okay. So I'll start looking at the big spheres first. And whoops. So here's a sphere, and then between this and this is a plate. And I think if I put on the yeah, see, now you can see the flathead screw that's just keeping it. There's no tension on it. That screw bottoms out in the threads, and you can see underneath it, it rides on that. But that flathead screw keeps it from falling out under. And then here's the other smaller ones. If you turn on the other parts, they sit there with another. These are 632s. That's a 1032, I think, on the big plates. So now I'm going to turn these all off, and we'll go back to the design. Now, what you notice on these three plates, the three big plates.
Dan, Rob Brown here. I didn't understand why you couldn't use an acorn nut. It seemed perfectly fine.
Well, because I needed to tap a hole in the end of it, and the acorn nuts that I tested, it's all hollow up there. They solder a little shell on top of it, so it wouldn't work. That's why.
I thought those were solid brass. They're not.
I did too. I mean, maybe there are some, but this way I can make them exactly the way I want them anyway, because it'd be hard to find that. But thank you for that question. And the other thing that I'm going to do is I'm going to make them out of oilite, and probably many of you know what that is. It's a bronze alloy that's impregnated with oil, I think, or graphite or something, and it's self-lubricating. So that'll be a big help too. We'll probably 3D print these little mirror contact points. And remember that part that I showed you that had the little plastic piece that slipped over a 632 thread? Well, see where my mouse is. One goes in there, one goes in there. That keeps this thing from tipping back and forth. One goes here and here. That keeps this plate from going, or, you know, turning. And then one here that keeps this plate from turning. And then there's two that are pointing down that go by the cell frame, which keeps the main plate from turning. And they're all like, all three are like that. So just those holes in the main plate keep everything steady. So that's one thing I thought about quite a bit. And then these are the mirror keepers right here. And you notice that this was on the side of this bracket here because of space requirements. And so that means if I turn on the mirror, you'll see the covers. But these are all 120 degrees apart. And that's why this one here is longer than this one here. And so that's the mirror keepers here. Now, there's also mirror adjusters. So if you look in the end of this, now this one was the first one I did, like this was my 28-inch telescope in the early 2000s. So this part right here is a piece of plastic, and it's got a threaded hole in the middle, and it's made to fit tightly inside this square stock. And on the bottom, there will be either a jam nut or what do you call those? It slips my mind right now. The kind that don't turn unless you really refine a nylock nut on the back. That's how I do my 28, and that's always worked really well on my 28-inch. And so I stuck with that part of the design. These are bearings. They're 1.25" bearings, I believe, and we're going to 3D print a piece of plastic that goes around them, some kind of material that Taj, he knows everything about 3D printers. He'll recommend what kind. It's got to be hard because we don't want it to compress. So whatever he says we'll use, we'll probably 3D that, so it won't be metal on glass. So before we leave the mirror cell section, does anybody have any comments or suggestions or questions?
Well, you answered all my questions in the course of your description.
Okay.
The one last thing I would ask is, are you planning on painting the cell or powder coating or what?
Yeah, we'll probably powder coat it because it's all steel.
Mm-hmm.
Yeah, I mean, I know that's what we'll do. Okay. So now we're going to switch to this is a slewing bearing. I showed you a picture from the factory. Now you see this dimension here. It's really meant to be this way. This is how it came as a drawing. And you can see that the outer ring is higher than the inner ring. And this dimension is about 32 inches. It's just under that dimension. That's how big this slewing bearing is. But we're going to use it this way, like that, because I want the outside part to be the most stable part that is, connected to the ground via the ground structure.
Dan, how much does one of the bearings cost?
Okay, so this one costs about $1,800 plus shipping. So this is a major part of the cost. Well, it's about the same as one of the encoders. Encoder is a little more, but it also weighs a lot. It weighs 275 pounds. But fortunately it's at the very bottom, so that's good. All right, so let's turn off some stuff here so you can see what it looks like on the inside. So there's bearing balls. I'll turn the balls off, and the groove, this is just a spherical groove, but the groove is shaped a little funny, so there's only 4 contact points. So that's the slewing bearing. I think we're done with that pretty much. Now we're going to see the motor. Now this motor, I've spent a lot of time designing this thing. This is a slewing part right here. Turning it off and on. And I'm going to turn it off so we can just try to imagine it. So it's upside down from where the factory had it, but they said it was okay to use it either way. This part right here connects. This part here turns. The part that's yellow turns, right? This part here connects the magnets to the part that turns. This part right here, okay? So now I'm going to turn this off so we can see the insides. Underneath is a piece of aluminum. It's 3/8 thick, and I was worried about, Dave Rowe says he gets paid to worry, and I really understand that. I didn't want any vibrations from the magnetism and the PWM of the magnetism and resonant frequency. So this is a 3/8 piece of aluminum. On top of that is a 1/8 piece of steel. And these are the coils right here. I'm going to just turn off some of this other stuff so you can see it. Okay, so this is a set of coils, and they're screwed onto the plate, right? So on top of that are the magnets. And remember, I was mentioning that, there's some friction component to this slewing bearing. Well, that's why I'm using a double motor on the azimuth. And so there's coils on the bottom, and there's coils on the top too. See that? And if I zoom in on this, you'll see a nice gap right there. Turn on the coil top plate. and the top plate connects the top coils, which are stationary. They're stationary. So this whole bottom part is stationary, and it holds this top plate right here, which is 3/16 steel, to these coils. So this motor is going to have twice the torque for a given current. And that will save on batteries, and it will save on and you know, we'll be able to use lower voltage, and it solves a lot of problems. Okay, so now I think everything is turned on. Let's see, most things are turned on. Okay, so now this is how we connect the rotor. I'll turn back on the slewing bearing. There we are. Okay, so one last thing to look at is this is the encoder bracket, and we designed these for the Atlas project. We made 2 mounts for the Atlas project, which you might have heard of. And if I turn this off, so we're going to water jet this plate. This is a 3/16 plate. I'll turn it back on. So this dovetails into there. And actually, Russ knows all about this, don't you, Russ?
Yeah, they work great. It's wonderful.
Yeah, so there's a spring between here and here. This is threaded right here. And then you can just turn that screw until you get a blue light on your encoder. And then you tighten these 2 set screws that lock it into the dove. And then this mechanism here is the only way I could think of to connect the ring, the encoder ring right here. This is the encoder ring to the rotor, because that has to turn. So these 3 things, I didn't draw the bolts in here, but that holds this steel plate right here, and that's bolted to the steel plate, and this is bolted to the ring. Any wires that come up can go through this center part. And so this is what I came up with. Now, I think I'm done with the motor. I should go back to it and ask if anybody has any questions or comments or suggestions.
Question, Dan, can you hear me?
Yeah, loud and clear.
Oh, great. So on the slewing bearings, are you okay with them without having a spacer or a carrier between them?
I guess I don't understand your question. A spacer or carrier between what?
Between the slewing bearings, the individual bearings.
Well,
Normally you would see in a configuration like a spacer so that the bearings don't touch each other because they're rotating.
oh, yeah, they
the ball
don't.
bearings.
Yeah.
Yeah.
Let me see if I can call up a PDF real quick. So this is
Normally they wouldn't touch it. Yeah.
So this is their drawing, and no, they don't touch each other. They only touch their balls, and then okay. And then there's a seal on the top and a seal on the bottom to keep out dust. So this is their drawing.
Right, but the bearings don't touch each other side to side. They're separated.
Oh, I see what you're saying. They're like a cage, a bearing cage.
Yeah, a bearing cage normally we would see to
Yeah.
keep them separated. Yeah.
Yeah, I think that I don't really know the answer to that question. All I know is that they gave me the frictional component, and that's why I made the double motor. So we'll have to see. Maybe they do cage them. I don't know. Anyway, that was a good question. Anybody else?
Just a thought, Dan. The structure you made to center the encoder ring, with the 3 arms and the circular cutout in the center, and then the encoder on the bottom. Couldn't you just do away with that if you're gonna water jet out the top ring? Why not just have the design arms coming from the inside edge of that ring to hold the encoder?
So make that ring longer. Well, one of the reasons it's higher.
Oh, it's higher. There you go.
Let's see.
Okay.
And let's see if
Question.
it could work. well, it has to be above this plate because that plate right there is
Yeah.
stationary, right?
Right.
And so the encoder, that's an interesting idea. I'll spend some time thinking about it. So I would have to lower the ring a lot, and then this is going to hit the ring, so I'd have to lower that to underneath. That's an interesting suggestion, and I never really approached it that way. And maybe I can do that because that would just be a bigger piece, or a different water jet cut.
Yeah, or maybe the encoder just sits on top of those arms instead of having to lower it down.
Yeah, that's what I'll look at that tomorrow and see if that's
Yeah,
going
it
to see if
looks
that
like
could work.
It could.
Yeah,
Anyway, just thought.
yeah, it's a good thought.
I'm going to ask a question that shows I really don't know what I'm talking about. But is there any way that encoder could look at the inside of a cylinder instead of the outside of a cylinder? Because I see opportunities.
I don't know if Renishaw makes an encoder like that. They make linear ones, but I've never seen one that goes on the inside. Yeah, I was wishing for that, to be honest.
And Dan, how do you center the encoder ring? Is that done by tweaking the tripod support?
Well, that's a really good suggestion, or good question too, Richard. And I've done this actually several times. And as Marty's here, I noticed Marty here. I'm going to be doing it again. And I laid on the floor at North Carolina. It must have been 6 hours, and it had a fairly slow slew speed. And I had to slew the telescope back and forth with a dial indicator, and make an adjustment and hope I got it right. And I ended up getting it so it was well within the tolerance, but it took a long time. And this has an advantage, Richard, where all these are going to be CNC milled, all these holes, and they're going to be very centered compared to this. And so let's see if I can turn that back on. So as long as I follow this procedure, it should be fairly close right to begin with. And nothing's perfect, and I'm going to have a way to adjust that. But that's a good question, and it might take some time.
It was a pain with the Cal Poly to center that, especially with the replacement ring.
Yes, I remember that.
Yeah.
Yes, yeah, it's always a challenge.
You could do 2 more little dovetail type devices. Since you already have the design, just make 2 more of them so you can move the thing back and forth in controllable small amounts and then lock it down.
That would be a real nice thing to do. I don't know, since they're not across from each other, it might be
But you could put them across from each other.
That was my first design.
Okay, 4 veins, and 2 of them are active and 2 of them are just loose sliders.
Yeah, my earlier design had 4 veins, so that's definitely a possibility and something I could think about. So I have 2 suggestions. That's nice. I love the suggestions.
Because you've already got the dovetail design and it works.
Yes.
And so you just make more of them when you're making them.
Well, we made 9 of them, so we have 9 of them now.
Okay.
Okay.
One more thought here. Could you spring load the reed head so that if the encoder was a little bit out of round, the reed head could just kind of travel along back and forth across the elliptical reed head?
Yeah, you know what? A follower. I tried that on my 28-inch scope. I tried to get an encoder on the altitude, and I had a mechanism that tried to follow it because nothing was ever centered. It had like a roller bearing that followed the track, and I couldn't get it to work reliably. But it's definitely a thought.
Okay.
See that we already have the dovetail, so if you had just a spring pressure and then you had a roller on there, that's an interesting idea. It might work in this case. So then there's two set screws, one that goes in there and one that goes in there. And in this case, we wouldn't use it. We would have to put a bearing over here and a bearing over here that would follow that. It's an interesting idea.
Well,
Now we
Dan, my suggestion is to make this as finicky and as tricky to get it right as possible. So you're constantly flying down to Chile. To
So I
help
can get some
Jimmy.
views, yeah.
Yes. That's my idea.
Yeah, okay. All right, so we're going to move on to the telescope now. I don't have too much to show here. Those are my two major pushes so far. My next major push is going to be the altitude motor, and I threw some stuff up there that's just kind of, you know, they're going to be those are the right sizes because that's our standard motor that we can make, and that's an encoder. This is one of my worries, you know, one of my Dave Rowe gets paid to worry is this. Let's see. Okay, so this is the coils, and this has to be very, very stiff, and I'm going up all this way without any support. Well, I don't think that's going to work. I need to support this because magnetism and PWM, or that's not going to be. It'll be not good. So.
Can you define PWM for everyone?
Oh, yeah, pulse width modulation. That's how most motor control systems work. They use PID, which is proportional integral derivative, and you position, you apply magnetism in exactly the right way so that it's always putting the torque to get the encoder to exactly where it's supposed to be at that particular time. And so that PWM just turns the transistors on and off for a varying amount of time. In an ideally balanced telescope with ideally low friction, they would be near zero net energy. But then if the telescope is out of balance, it'll always be applying a torque one way or the other. And then so these are everything below this surface, this yellow surface here, everything below that is steel. I like steel. It's easy to weld. It's really strong, and it's lighter than aluminum for a given stiffness. Sometimes that doesn't work out so well because it could be too thin, and aluminum can be thicker, so you can actually tap a hole in it. So, but that's kind of the philosophy. And I wouldn't call this a true Serrier truss because the poles are going to be they're going to be aluminum instead of steel. These are going to be steel down here, but it should help in some of the sag anyway. This is going to be fairly conventional at the top, the secondary cage. And these are going to be 2 1/4 inch pieces of aluminum. And I haven't designed the keepers for here and there. These rings look a little anemic. They'll probably be bigger, I don't know. And then I'll probably use some channels instead of this, especially by the eyepiece and the focuser. And I'll use a conventional spider, probably from, I forget the name of the company.
Astro Systems.
Thank you. And then I think he wants a feather touch focuser. Wasn't that it, Howard?
Mm-hmm. Yeah. And he'll want that focuser on the other side of the cage too.
You can put it on either side because all you got to do is is pivot it the other way, so you can just make it go over the other way. I spun this on this axis. I think I won't take the time because we're probably kind of late already.
We're a little late, but that's okay. We started a little late too.
Okay. I have a few more slides.
I have a question. I just have a general question about these direct drive motors. And you might not want to consider this for this job, but is there any reason why the altitude motor has to be a full circle? Because the scope is only going to go 0 to 90.
That's a good question. You're right. You only need a few magnets. You could do it with just a few and coils. Although you'll be better off with torque if you use all of them. But that's an interesting thing. That gives me an idea, Rob. So what if I was to make a half a motor and make a double half a motor? So then I could have it all supported by this bottom part, and then I wouldn't have this up in the air stuff here.
Exactly. I'm thinking about the next super lightweight, smaller scope that really is portable, that maybe can make use of such motors if they didn't have to be a full circle.
Yeah, yeah, we've thought about that in the past a lot, but I didn't think about it until this moment. So thank you for that. So I've already got several suggestions here, and that's one thing I'll look at, making a double partial motor to try to get rid of the bracing up at the top end. So that's an interesting idea. So anybody else comments before we move on?
Yeah, I have a question that was typed in on the chat function from Akers, and he's wondering what is the pointing accuracy you expect before you make a point XP model and then after the model is built?
Okay, I think that's a good question, and I have a fair amount of experience with different kinds of things, and you can tell a good telescope mount right off the bat. You just turn off all the terms except for polar alignment, and you can just see, hey, this is a pretty darn good telescope mount, or the opposite of that. And I'm inclined to believe that this is going to be a pretty good telescope mount. So I'm going to guess that we'll achieve 30 arc seconds. We'll definitely be less than an arc minute without a model. That means that if you plop this down on the ground and you make it level, and you know it's level, and you enter the latitude and longitude, and you sync on one star and you don't have a model, you'll probably be able to go within an arc minute anywhere in the sky.
Dan, do you have 3 feet or 4 feet for the telescope over there?
Okay, good question, Tong. In fact, I was going to say that. I almost forgot to say that. So, whoops. Come on, what happened? All right. So these are the 4 feet, and they're going to be screwed feet, so they can go up and down. Now these discs, I initially drew them just as a disc so you could reach down and adjust them to level it, right? Now here's my idea right now. It's instead of a disc that you reach down and turn, it's going to be a 3D printed timing pulley. And the timing pulley is going to have great big thick walls, long walls, so that the belt will never become disengaged. And then there will be a timing belt that goes around all 4.
Mm.
So if you loosen the timing, you can just use a drill motor with a timing pulley on the end, and you can like turn all 4 at once and raise it or lower it onto the wheels, the portable wheels, which I haven't drawn yet. And so to answer your question, Tong, there's 4.
Okay, so,
yeah.
So how do you make sure it's all balanced? It's equally distributed.
Well, you just use your level, and
okay.
you can feel the torque and
okay.
And, yeah. I do this on my, I have 6 on my 28, and you know I spend a little time leveling it. Yeah, but
okay.
yeah. Okay. Anyway, one of the things I wanted to say is this is kind of a unique telescope in a sense, because it is sort of bridging the gap between professional telescopes and amateur telescopes. So it's kind of a unique position, I feel. Okay. Any other questions before I move back to the?
Yeah, one more question on pointing. Does the temperature change impact the stability of the pointing?
Well, yes, for sure. but hopefully a very small amount. One of the things is the encoder's read head is mounted on steel, and it contracts and expands both ways, left and right. So that should not be a problem. Let's see. It will change the length of the tubes. I don't think that's going to be very consequential. So I don't know. I would guess not very much.
Yeah, I'd like to ask one little question. Since this is being used by a guy with a ladder who's sometimes up on the ladder, and from the Cal Poly, which we could slew at 60 degrees a second, I wonder if you could incorporate some bumper bars or something so that when this upper end of the tube collides with something like the ladder or the observer, it shuts off the power to the motors, or the motors are tuned in such a way that as soon as there's a significant over current, it de-energizes and doesn't push him off that 14-foot ladder.
Yeah, that's a good point. Well,
so, can I say something for a sec?
Yeah.
So in some of the microscopes I work on with that are SEMs, they have a collision detection system, and what they do is they put a small charge on the stage, and if the stage bumps into anything, it basically shorts that out. So if he's on an aluminum ladder and you've got steel trusses or metal trusses, you could put a digital signal between the two, and if it hits the ladder, everything shuts down.
Yeah, you know what? Those are really good points, and this is going to be a tall telescope. I think I have a eyepiece height here. We can take a look at that. And this eyepiece height, if you look down here, it's 145 inches. So let's do that in feet here. 145 divided by 12 equal
12.1, 12 foot 1 inch.
Yeah. Yeah, so that's I wouldn't want to take a fall that high. You know what, another thing that I used to do a lot of quadcopter stuff, and one of the things we used was a sonic sensor. And we could use a sonic sensor and stop it before it even hits somebody.
Yeah, that's exactly what you want to do. You don't want to have a collision, or at least you don't want to have a collision with anything that's solid.
Yeah.
The Cal Poly, when you was slewing it at 60 degrees a second, you really would not want to have been looking into an eyepiece if you accidentally hit the wrong button. And instead of going away from you, it came towards you.
Yeah, yeah.
And it was a pushy beast. It took a lot of force to make it stop.
Okay, I'm trying to write some of these things down. Let's summarize. So somebody had the idea about the encoder. Oh, that was Howard. Encoder ring mount. What was some of the other ideas? I thought I wouldn't forget them, and now I've already forgotten them.
The altitude direct drive motor not being the full circle.
Okay. Partial altitude motor. Okay.
Having a dovetail so that the encoder could just follow the ellipse.
Dan, since I'm just not quite convinced it's a direct drive motor is suitable for visual observing. At this point, because the speed wise, you really don't need the speed, right?
No, they would. I suspect he'll have it running pretty slowly.
Yes, it's
he won't run it at 60 degrees a second. I'm supposing he'll probably do.
Yeah. So what is wrong with the drive system Howard it has been working on with. So can you compare with the two drive system? What's the advantage over Howard's drive system you can achieve for the visual observing?
Okay, well, Howard doesn't ever use go-to. Howard just pushes his telescope around, and he knows the sky by heart, or he uses a map. Am I right, Howard?
That's right. Yeah.
Yeah. So he uses the control system to track, and that's it.
But that's available. The go-to is available. It's just not using it, but it's readily available, right?
Yeah,
Oh,
but it's not nearly as accurate as this. It's by far. I mean, struggling to do an offset sync on a nearby star, centering that star, syncing, and then moving over to the double star you want to take the images of. And then it drifts out of the field of view while you're doing it. Of course, that's not visual, but visual. The way that Jimi observes is high power all the time, and he won't ever have to put a low power eyepiece in to find something. So that's going to be the main advantage of this.
I agree with that. Even for visual observing, I feel that, when you're looking at distant galaxy groups and so on and so forth, you want a pointing accuracy that's within maybe 10 arc minutes or 5 arc minutes. And at least currently his telescope has doesn't hit directly. He has to always go to a local star and do a sync. And I think that's the major advantage, right?
Yeah, that is. He'll be able to keep that 500 power or whatever power eyepiece is, and it will be 900 power, 1,000 power eyepiece, and it will be there, because we're going to be pointing. If he makes a 16-point model, my guess is he'll be under 10 arc seconds, because of point XP. He'll be able to point that thing within 10 arc seconds, and he uses go-to. He uses oh God, what's the name of that software he uses?
Megastar.
Megastar, and he finds the things he wants to look at, and he does a go-to to him. He's going to love this compared to the other one. I guarantee it.
Howard, have you ever tried use go-to function with your scope?
Oh yeah, a few times.
It works. It works.
Dan has helped me each time I've done it, and we've made a model, and it points wonderfully well.
So what's the accuracy you get with your scope?
No, it's not 10 arc seconds, that's for sure. I would say it's about an arc minute.
Yeah, okay. That's about what I get with my 28 before I'm doing these mods to make it direct drive. I'm getting about, I consider it lucky if I get an arc minute model.
Yeah.
Yeah, you guys are talking about some tiny numbers here. I have a 12.5-inch 10 Seggerty that is just sloppy. And, I'm happy if I'm 5 arc minutes, and typically more like 15 arc minutes for visual observing at low power. And that's the difference here. At low power, it's fine. It works wonderfully. Yeah. But, I'm at 100x, not 1,000. So,
yeah.
So if the pointing accuracy is not that critical, right? So as long as it's tracking well. And what's the difference between the 1 arc minutes and the a few arc seconds for visual observer?
It depends on how much magnification you're using.
Okay.
And because Jimmy's always using well above 500 power, assuming it's a decent night, he's going to keep that 500 power eyepiece in the focuser. If he doesn't have to search for his next target when he does his next go-to, which is pretty much what he has to do now on his 48-inch. And my prediction right now is that after Dan's finished building this 36-inch scope for Jimi, and Jimmy's taken it down to Chile, and he's used it, he's going to call Dan up again and say, hey, Dan, I want you to rebuild my 48-inch with direct drive motors.
Okay.
That's my prediction.
Okay, I see.
Okay. I might venture a slightly snide comment, since you can rotate the secondary to 2 different focus positions. Put an imager at the other one. And since the software for Stack and Track is now becoming mature, you know, after Jimmy's looked at this thing and squinted and tried really hard to see this 18.5 magnitude thing that he's looking for, he could spin the thing around and shoot 60 seconds perfectly tracked and go to 23rd magnitude.
I don't think you know Jimmy.
He might bump his head. Who knows? Yeah.
I know people like Jimmy. You know, sometimes they undergo a religious conversion when they suddenly discover 90% quantum efficiency sensors and what they can do in 60 seconds. You know, could happen.
You never know. Yeah.
Yeah. So, you know what? I think you misunderstood me. I'm not, this doesn't have a rotating secondary for 2 points. You would have to put that in there. It could be part of the design, but what I meant is he could view it with either side of the, you know, I had it at 45 degrees. Let's say it was pointed to the west. You could also, without moving the azimuth, point it to the east. That's what I was talking about.
Okay. Okay.
Okay.
So we're about a half hour behind our timeline right now, Dan. So
yeah. I'm going to go fast. Yeah.
Okay.
Okay. I'm going to rebuild my 28-inch with direct drives. And let's see here. I'm going to use I have a direct drive on the azimuth already. And I can use the existing mirror frame and mirror cell. I have to make a fork similar to Jimmy's. I'm going to do away with the strings and the folding secondary and add a rotator and focuser, which brings me to this slide. This is a bearing. I bought 2 of these from VXB, and they cost, if you look over here, they cost $17.30, $17.37. And they were remarkably, one of them was remarkably good quality. The other one was a little sloppy, so I don't know why there's different, but I started printing out, these are the scraps. Rob will appreciate this. These are the attempts at the, shoot, I can't think of the word. Anyway, then, you know, Taj is the expert at 3D printing, and he printed these for me. These are 3D printed timing belts. And so here's the more or less finished. So there's 1, 2, 3, 4 parts, and then there's one inside here that this black thing pushes against to put this roller on this Crayford design focuser. I designed it big enough so that a CWO camera will fit in one end. Whoops. That's my last slide, but I have one more short little video. This thing, I'm pretty excited about it. This is for my 28-inch telescope. And I started thinking about this, and, you know, for some dollars worth of PLA 3D printing filament and a couple of bearings and you know, a couple of aluminum pieces. Let's see, I'll try to speed this up. Okay, so that's the timing gear, and it works really well, as you'll see in a moment. Look at that. Okay, it should start turning here real soon. Okay, it's a bad video, sorry. And it turns really fast, so if you have a direct drive telescope, it'll keep up with it. To keep north up or whatever you want to do. And then the focuser works too. I'll fast forward. Okay, there's the focuser. All right, the focus is going to start moving here, so watch closely. There's the 3D printed timing belt. Okay, there it goes. And there it's moving in and out. So anyway, this is for my 28-inch telescope, and I'm pretty sure it's going to work just fine. And I do believe that that's the end of my presentation. I was going to say questions, but I think we're out of time.
Well, we've had a lot of questions along the way. So yeah, I think that's good. Well, excellent. That's exciting stuff. I can't wait until you get to the point where you're actually building this thing.
Yeah, well, we got, I forgot to mention, we have all the motor parts for the azimuth motor ordered. They're going to be here in a couple weeks. So that's good. and then we'll start working. So I'm going to mute my mic.
Okay, very good, Dave.
Okay, well, Dan, why don't you take your quick 5 minutes here to update us about the breakthrough you had for Jimi's 36-inch, based on comments you received on Thursday.
Okay, can you guys hear me?
Yeah.
Okay, I got to figure out how to share my screen. I'm pretty slow at this. Share screen. Okay, you're always going to see a double image. Okay, here we are. Oh, that's programmed. Okay, minimize, minimize, minimize. All right, so this is all done with FreeCAD. Let's see if this is it. Let's see. Okay, so I've known this for many, many years, that you don't have to make a circle to make a motor. You can make a linear motor with, or you can make an arc of a motor, and it'll work just fine. But I forgot about that. And then Rob Brown made a comment about, and I had a problem on this design. I had to figure out how to support the magnetics way up high, way higher than the axis of the altitude axis. And he said, well, why didn't you do that? So I made because of what he said, I made an arc. So let's start turning on some of this stuff. Okay, so this is the fork here. Dave, you didn't see the whole model of the other telescope that I gave on Thursday night. But so then I made this. This was on Saturday. I pretty much designed this, or Friday and Saturday. And so since I wanted to not have anything up here where my mouse is, flapping in the wind, so to speak, I wanted it all to be solidly to the fork. And so I instead of doing that, I made a dual motor. So these blue things here that you can see are coils, and then these are the magnets. So it's a dual motor. So it's about 9 coils instead of, I think, 24. So it's not 180, but this will turn 180. That's what these sections of the magnets are for. So you can turn the full 90 degrees that an alt-az telescope needs to move. But it's all down here and all backed up by solid structure. And so that was a really good thing. Thanks, Dave. Thanks, Rob. Are you here, Rob? Rob's not here tonight. Okay. So then on Sunday, no, this would have been Saturday, I got a call from Joe. Are you here, Joe? Joe LaCour? Yeah, Joe's here. I see him.
I'm here.
Okay. And he said, well, why don't you put the magnets all and the coils underneath the mirror for the altitude? And, well, that has a huge advantage. First of all, leverage, and then second of all, you can put it in the center so it doesn't try to twist the frame. And twisting is a huge thing. So if the structure twists, and I have some experience with that, it's really hard to control. You need to use a notch filter, and even then it's just a mess. And so that was one of my worries. I didn't want to do that because, you got to make it taller, and you got to have all these big coils of, So, but he got to me thinking, and it wasn't until this morning I thought of this. So he gave me the idea. I went back to a 1-layer motor. So there's the coils, and then there's the magnets, but I put one on each fork. Now the advantage of that is you put a torque on one motor, you're also applying it to the other motor at the same time. I mean, instantly. And so there could be a little flex in the mass of the mirror and so forth of lag, but it's going to be way better than if you're trying to just twist with one motor on one side. And so I'm just going to do it. It's going to be so much better. And it, like I said the other night, I said, I get paid to worry. And just like Dave Rowe says, he says he gets paid to worry. And, you know, I feel the same way. And this is one big worry off my mind. And it's because of this workshop here and some comments that we got. So that's it for me. I just wanted to show that off.
That's really cool. That's really cool. That's the kind of thing that makes this feel like a workshop.
Yeah.
Okay. Ed Allen, are you out there?
I'm here, Howard.
Okay, Ed, you're up. Updated clutch system.